nomenclature or naming compounds. That's what we're going to cover in this lesson, and we're not going to name every compound in the universe, but we're going to name 3 specific types of compounds. So ionic compounds, molecular compounds, and then a couple different types of acids. Now, this is the final lesson in a chapter on atoms, molecules, and ions in my brand new high school chemistry playlist, and I'll be releasing these lessons weekly throughout the 2020-21 school year. So if you don't want to miss one of these, subscribe to the channel, click on the bell notifications. You'll be notified every time I put one of these up. Okay, so before we can talk about naming compounds, it turns out you got to find out how to identify these 3 types of compounds, ionic, molecular, and acids. And the reason that is because we actually use different sets of rules for naming compounds depending on which type of compound you have. So if we look first at ionic compounds, so ionic compounds generally like to think of as being a metal with a non-metal. And so that's what we had to talk about in the periodic table lesson last one, the division between metals to the left of this imaginary staircase and non-metals up here to the right. And so good example, most famous ionic compound probably of all time is sodium over here, a metal, with chlorine right here, a non-metal. Cool, and that's a classic example of an ionic compound. And I personally like this example because a lot of students already know this is sodium chloride. And if you already know the name, it's going to make learning the rules for a name you already know that much easier to apply to the rest. Cool, then we'll move on to molecular compounds. And molecular compounds generally are going to be non-metal with non-metal. And so we're just going to pick a couple of different non-metals here. Now, it turns out these molecular compounds can have more than 2 types of elements, but we're only going to learn how to name those that have exactly 2 types of elements. So we call them binary compounds. And again, there are more complex molecular compounds. We're just not going to cover naming them in this lesson. We're going to stick simple and just learn how to name binary molecular compounds. Cool. And then we're going to learn how to, let's give an example, by the way. So things like carbon dioxide would be a great example. So carbon is a non-metal, oxygen's a non-metal, and carbon dioxide is going to be a classic molecular compound. Cool, finally acids. So identifying an acid, most compounds where the first element listed is an H can be classed as an acid. So most famous acid of all time is not LSD, it's hydrochloric acid. So get your mind out of the gutter. So HCl, hydrochloric acid, notice it starts with an H, and we call this a binary acid. Notice that name binary coming back up, and binary acids are one of the 2 types of acids we'll learn how to name, and the other type of acid we'll learn how to name are called oxyacids or oxoacids, and they're going to still start with hydrogen, but they're also going to have oxygen in there. Now, we'll find out much later in this course that there are acids that actually don't begin with an H in their formula. So however, we're not going to encounter any of those in this chapter whatsoever. In fact, in a typical high school class, you might not encounter them ever. So I'll probably allude to them once in a chapter late in this course on acids and bases, but I'll allude to it briefly. Like I said, good chance in high school you won't even come across that other form of acid. All right, so now that we've learned how to recognize the different types of compounds, now we can go through and talk about the different sets of rules for naming every single one of these types. And we'll definitely start with ionic compounds. All right, so before we can dive into naming ionic compounds, it becomes important to realize that there are certain ions you can predict their charge based on where they're located on the periodic table. So it turns out these noble gases here, they are the coolest elements on the periodic table, and everybody, if they can, wants to look like a noble gas. And what I mean is that everybody wants to have the same number of electrons as a noble gas. Now, the noble gases are always neutral atoms. We're never going to see ions with the noble gases. And so in the case of neutral atoms, that means that your atomic number here not only gives you the number of protons in the nucleus, but as long as we only have neutral atoms, it also gives you the number of electrons in the electron cloud. And so in this case, like neon's got 10 electrons. And fluorine's just like, dude, neon's so cool. I wish I was as cool as neon's. I mean, as a neutral fluorine atom, I've only got 9 electrons. Neon's got 10. Oh, I just wish I could look like neon. Well, that makes gaining 1 electron for fluorine a very likely occurrence. And the most common ion that fluorine's atoms will form is a -1 ion, 1 additional electron. Whereas for oxygen, which only has 8 electrons for a neutral atom, he wants to gain 2 electrons to look like neon. And so the most common ion you'll see oxygen forming will have a -2 charge. For nitrogen, it would be a -3 charge. And so we'll find out for the nonmetals, their most likely route of having having the same number of electrons as a noble gas is to gain electrons and have a negative charge. But for metals, it works the other way around. So, and there's only really two columns of metals. There's two groups that you already know, the alkali metals and the alkaline earth metals. Those are the only ones that you really got to know what common charges they take when they are ions. Now, again, we can have neutral atoms, but when they're an ion, we know what charge they're going to take. Now, if we look at, say, sodium here, sodium's got, as a neutral atom, 11 protons, 11 electrons. And he looks back and says, shoot, neon is the closest noble gas to me. I just wish I could look like neon. And in his case, he's got too many electrons, having 11. He's got to lose one. And so when sodium loses an electron, he ends up with a positive charge, a +1 charge. And so it turns out that's the same way for all the group 1 metals. Sodium wants to look like neon, lose an electron. Potassium with 19 electrons wants to lose one to look like argon with 18, so on and so forth. So the alkali metals, the most common ion they form by far, in fact the only ion they form, is a +1 ion. The alkaline earth metals in the same sense, so look at magnesium here with 12, atomic number 12. A neutral atom would have 12 electrons then as well. Well, he wants to have 10. And so the most common ion that magnesium forms will be a +2 charge, losing 2 electrons. So the alkaline earth metals in general as ions will be +2. So again, all of these atoms, they can exist as neutral atoms as well. But when they are ions, the alkali metals are always going to be +1 and the alkaline earth metals are always going to be +2. Cool. Now the transition metals are a pain in the butt, and we're going to have to learn how to name compounds using the transition metals. And the problem is you can't look at the periodic table and know what charge they're going to have. Like you can't look over here and be like, well, what charge does zinc have? Well, turns out zinc is always +2 as an ion, but you can't tell that by looking at the periodic table. I know that from memory. Same thing, copper right here. It turns out copper actually has 2 common charges, +1 and +2. And again, I've memorized that because I've worked in the field for so long. But there's no way to look at the periodic table and be able to predict that. Iron, 2 common charges as well, +2 and +3. Again, pure memorization on my part, nothing you could ever predict by looking at the periodic table. We'll find out that's going to be important in how we name compounds in a little bit. All right, so let's take a look at the rules for naming an ionic compound. So if you look at the formula for an ionic compound, it will always have the metal first, the non-metal second. So oftentimes we will call the metal, which will have a positive charge as an ion, the cation. Cation simply means a positive ion, positively charged ion. Whereas the non-metal, so like we said, chlorine wants to be -1 to look like a noble gas. So the non-metals are going to have negative charges, and we refer to those as anions. And so for an ionic compound, you always have cations paired with anions, positively charged ions paired with negatively charged ions. And so you're always going to name the cation first. And so when you've got a metal as your cation, you just simply give the name of the metal, and Na is sodium. Cool. Okay, great. You just say its name. That's word number 1. Cool. Now, as long as your metal here is in group 1 or group 2, then you already know its charge. In fact, sodium, because he's sodium, in an ionic compound, he has to be +1 every time. So that's good. So we'll find out then, we can skip rule number 2 for anybody in these first 2 groups. Because we already know their charge, they have to be the same charge every time. Rule number 2, which talks about putting the charge in parentheses of the cation, is not needed in this case. All right, so then you move on to rule number 3, and rule number 3 says name the nonmetal. And in this case, Cl stands for chlorine, but it specifically says name the nonmetal with an IDE ending. So instead of saying sodium chlorine, we say sodium chloride. Cool, we'll see this is a common pattern where you name the second element with an ID ending, not just for ionic compounds, but also for molecular compounds as well. Cool, and that's sodium chloride. We just went through the nomenclature. So name the metal, sodium. Skip rule number 2 in this case, not needed. So because he's a group 1 or group 2 metal, and then name the second element with an IDE ending. Now, it turns out one thing, and this is pretty technical, and we do teach this to college students. Sometimes we're just like, maybe I shouldn't teach this to high school students, or maybe I should just never ask high school students about this. So, but your group 1 metals are always +1 in ionic compounds. Your group 2 metals are always +2. However, it turns out there are 4 other metals that always get the same charge. So it turns out aluminum is always +3, and that makes sense, going 13 back to 10, +3. So as an ion, aluminum is always going to have a +3 charge. That's not so bad, but the next 3 are not so great. So it turns out zinc and cadmium are always +2, and silver here, Ag, is always +1. Now, there's no way to look at these three on the periodic table and know that zinc and cadmium as ions are always +2 and silver is always +1 as an ion. There's no way to know that. It's pure memorization. However, for our college students, we totally make them memorize this. So because these four metals always have the same charge, and you're on the hook for memorizing that charge, those also are exempt from rule number 2. You don't put the charge, or oxidation state we call it, of the metal in parentheses for group 1, group 2, or aluminum, zinc, cadmium, or silver. All the rest of these though in here and down here and stuff, all those metals, we'll have to do rule number 2, as we'll see in a couple of examples here. All right, so let's go to the next example on your study guide there. We'll look at MgCl2. Rule number 1, name the cation, magnesium. Great. Cool, magnesium being in group 2 has to have a +2 charge. No ifs, ands, or buts. Has to have a +2 charge. So, and if you notice, your charges are always going to be balanced. So we didn't really worry about it too much with sodium chloride here, but sodium was going to have a +1 charge, and chlorine was going to have a -1 charge. And you'll find out in a properly written ionic compound, the charges will always balance out to 0. Same thing's happening here in magnesium chloride. So magnesium here is +2, being an alkaline earth metal. And then chloride being -1, that's why there's 2 of them. There's 2 of them that are -1 each for a total of a -2 charge to balance out the +2 charge we had on the magnesium. So, and that's going to be true of every ionic compound we look at. They're always going to balance out to 0 overall charge. All right, so we've got magnesium, first word, name the metal, name the cation. So, and we just figured out that the rule number 2, which requires us to put a charge of parentheses, is not needed since this is a group 2 metal. So we'll move on to rule number 3, which again just says name the nonmetal or name the anion with an IDE ending. So again, instead of saying chlorine, we're going to once again say chloride. Cool, and this is magnesium chloride. Now notice a proper name should work in both directions. Now we're starting with formula and working on names, but you might be required to do the exact opposite as well and be given a name and have to go back to a formula. And you'd have to look at magnesium chloride, and you'd look at magnesium and be like, oh yeah, magnesium's +2. And then you'd look at chloride and be like, oh yeah, needs to gain 1 electron to look like a noble gas. Chloride's -1. And you'd look at that and be like, oh, so magnesium chloride just can't be like plain old MgCl. It needs to be MgCl2. That way we've got 2 -1 chlorides to balance out the 1 +2 magnesium. Cool. So again, we're starting with formulas and going to names, but again, you should be prepared to go backwards as well. All right, next one on our list is CuS. So Cu, it turns out, cupra is the Latin root, and that's where copper comes from, and they sound similar, so it's not so bad. So, but again, one of those symbols you got to know for those first 30, and so this is copper, and rule number 1 says name the metal, name the cation. All right, so copper. Cool. Rule number 2 is going to be required. So again, we don't use rule number 2 for group 1s, group 2s, and then aluminum, zinc, cadmium, or silver. But for copper and the rest of these transition metals, and some of these under the staircase here, we totally are going to have to do rule number 2. And rule number 2 says, give the charge, or we call it the oxidation state, same thing as charge, of the metal in parentheses. And so we're going to save some room for parentheses here, and I'm going to come back to that in a second. And then, just like we've done before, rule number 3, give the name of the anion, the nonmetal, with an IDE ending. Now, S here is sulfur, but we're going to say sulfide with that IDE ending. Cool, now we got to worry about charge. So, and you're going to figure out this lovely metal's charge based on the anion we're with here in this case. And so sulfur here would love to look like argon, and as a result, sulfur needs to gain 2 electrons. And so your sulfur ion has in fact, I'll just put it over here, has a -2 charge. And if sulfur is -2, then copper, since these are in a 1-to-1 ratio, copper is going to have a +2 charge to make this work. And where we put that is we use a Roman numeral 2 in parentheses. And so if you just called this copper sulfide, that would not be good enough. You've got to call it copper 2 sulfide. Now, to show you that copper sulfide would not be a sufficient name, I'm going to give you another compound that would be called copper sulfide if we didn't have this rule number 2. That's why the rule is there, because we can't have 2 compounds with the same name. They've got to have distinct names here. So in this case, again, we're going to name the metal first and say copper. And rule number 3, if we finish this off, would still end by saying the nonmetal sulfide. Let's make that U look a little better. What's going to be different here is the Roman numeral that goes in parentheses, because here our copper is going to have a different charge. Again, sulfur here still has a -2 charge, but now these coppers, there's 2 of them. And so these 2 coppers are only +1 in charge each. And so the copper up here, again, was +2, and that's where the Roman numeral came from. But each copper atom here, or ion here, is only +1. And so we'll put the Roman numeral 1 in parentheses instead. And so we got to be careful here, because notice the 1 and the 2 don't refer to how many copper, ions are in the formula. It refers to the charge on each copper ion in the formula instead. All right, let's do a couple more here. Get a couple other examples. All right, so we've only dealt with naming binary ionic compounds so far. So, however, with ionic compounds, we also have to name those that have what are called polyatomic ions. Now, a polyatomic ion, poly means many, atomic, many atoms. And so these are ions that have many atoms in there. So, and I put probably a dozen or so, maybe 15 on your study guide, and I'll put them up on the screen here on the far right here so you can see them. So, you need to memorize these. No ifs, ands, or buts. You need to memorize all of them. And you need to memorize 3 aspects to each of these polyatomic ions. You need to memorize their formula, their charge, and their name. All 3 of those are important. So if you remember that SO4 is sulfate, that's not enough. You got to remember that SO4 with a -2 charge is sulfate. Super important. So again, the name, the formula, the charge, all 3 super important for these polyatomic ions. So when you look here, when you've got a polyatomic ion, instead of naming the metal, you just name the polyatomic cation. If you have a polyatomic anion, then instead of naming the nonmetal, you just name the polyatomic anion for rule number 3 instead. So, but in this case, it's the cation that's polyatomic. And so instead of naming the metal as the cation, you're just going to name the polyatomic ion, and NH4 stands for ammonium. Cool. And when you've got a polyatomic cation here, so it's not a metal, and so you don't have to worry about rule number 2 because it's not even a metal. Rule number 2 only applies to metals that are not group 1, not group 2, not aluminum, not cadmium, not zinc, not silver. So cool. So don't have to worry about rule number 2 either. And in this case, the nonmetal bromine, but again with an IDE ending, and this is ammonium bromide. All right, so we'll move on to one last example here. So this is CuSO4. And again, now we've got a polyatomic anion instead. So we always start with naming the cation. In this case, it's a simple metal, and we say copper. And because it's copper, just like we did above, copper can take on a variety of different charges. And so it's not going to be sufficient if we don't use parentheses here. We need those parentheses. And then we give the name of the polyatomic ion. And SO4 with a -2 charge, that's sulfate. Not to be confused with sulfite, which is SO3 with a -2 charge. So you really got to memorize the names, formulas, and charges of those polyatomic ions. Now, once again, this is why you have to memorize those charges, because sulfate has overall a -2 charge. And since it's 1 to 1, there's 1 SO4 for every 1 copper. Therefore, the copper must have a +2 charge, and that's why this is copper 2 sulfate. Cool. And this pretty much sums up ionic nomenclature. Now, one thing I didn't really get an example of here, is when you've got more than 1 polyatomic ion in your formula. So let's say I gave you ammonium sulfide. Well, ammonium sulfide does not have this formula, so because the ammonium is +1, and the sulfur being monatomic is just -2 based on where he is in the periodic table, and so this would not be a proper formula. I need 2 of these ammoniums, to go with the sulfur. Well, it would look pretty crazy if I just decided to put a 2 right here. That would look like NH42. Well, that's not going to work. And so when you've got more than 1 polyatomic ion, you need to put the whole thing in parentheses before you put how many there are in the formula. Now, if there's only one, you don't need to put parentheses. But when there's more than one of the entire polyatomic ion, that's when you'll use parentheses and then signify how many there are in that formula. Cool. So we didn't name an example like that, but I just want to make sure you had seen one before we move on. All right, so now we'll move on to talking about naming molecular compounds. And again, molecular compounds, you identify them because they're made of all non-metals. And again, we're only going to be dealing with naming binary molecular compounds, so we're only going to ever have two different elements involved in our formulas. And the way this works, I wish that we just used the molecular system for ionic compounds as well, but we don't. So because it's actually a much easier system. But the truth is, if we tried to use the ionic system of nomenclature for these molecular compounds, it would be a huge pain in the butt. We saw with like copper sulfide that, you might have CuS or Cu2S, and the charge on copper is different in both cases. But there's only two examples. There's copper 1 sulfide and copper 2 sulfide. Well, it turns out you can mix nitrogen and oxygen in like 7 different combinations. And so having to use like parentheses for oxidation states, it would just be a nightmare. So they said, okay, scrap it. We're still going to name the first element first. We can't call it a cation anymore. We don't have ions anymore. It's not ionic. So you name the first element first and the second element second, and you still name the second element with an IDE ending. But you have to tell me how many of each element you have with a numerical prefix. So mono for 1, di for 2, tri for 3, and I'm putting this up on the board as we speak. Tetra for 4. You might recall the game Tetris. Maybe you're not old enough to remember Tetris, but Tetris, everything that fell down the screen that you had to kind of organize was composed of 4 blocks. Tetra means 4. So it's not like quattro, or it's tetra for 4. Penta for 5, hexa for 6, hepta for 7, octa for 8, like octagon, nona for 9, deca for 10, like a decade is 10 years. Cool. You have to know those lovely numerical prefixes. And so before you name each element, you got to put a little prefix on the front of that word. So before we say nitrogen, you got to tell me that there's 2 nitrogens. And so instead of just plain old nitrogen, we got to say dinitrogen. Cool. The di prefix just showing me that there's 2 nitrogens in the formula. And before we say oxide, so again with the second element, you're still going to end it with an ID ending. So we don't say oxygen, we say oxide. But before you tell me that you say oxide, you got to tell me there's 4 of them. And again, that prefix is tetra. And so we're going to say tetraoxide. Problem is that a lot of times you're going to find that we do not like a vowel sound. And the tetraoxide, it goes and they just think that sounds horrible, and so they usually drop that first vowel and just make this tetroxide. And most of the time that happens when you have a vowel, when you go from prefix to element. So just keep that in mind. That's going to get dropped a lot, but usually that's not going to be like the difference maker of why you get like a multiple choice question right or wrong. Now, if you're doing a fill in the blank, well, sorry. But definitely worth your time knowing when to drop that lovely vowel here. Cool, but this is dinitrogen tetroxide. Life is good. Now let's take a look at another one here. So let's say we give you N2O. So with N2O, again, started off the same way. In fact, actually, I shouldn't do N2O yet because we should follow your handout. So we should do CO2. All right, so there's just 1 carbon. But it turns out the vast majority of molecular compounds have just 1 of the first element. And because the vast majority do, they just decided to make that the default. And they're just like, okay, there's only 1 of the first element, leave the prefix off. Since most of them have 1, we'll know what you mean. Okay, so we're not going to say monocarbon for that first element. We're just going to say carbon. And keep in mind, this is probably, again, a formula you probably have seen somewhere before, like in your biology class. But this is carbon, and then there's 2 oxides, so dioxide, again, ending it with an IDE ending. Cool. So if there's only 1 of the first element, no prefix is used. And that's going to be the vast majority of molecular compounds will follow that pattern. Now, however, if there's 1 of the second element, so there's no vast majority here. That happens sometimes, but most of the time it usually doesn't. And, so if there's only 1 of the second element, you've got to use that mono prefix for 1. And so in this case, this is carbon monoxide, the poisonous, lovely gas. And so when you've only got 1 of the first element, no prefix, but when you've only got 1 of the second one, you better, by all means, put that prefix on there. And so this would be carbon monoxide. But again, double vowel. And so instead of saying monooxide, we drop that first O. In fact, I'm just going to draw a big O instead of erasing it and bringing it together. That's carbon monoxide. And again, another place where we drop a vowel. All right, we'll do one last example. Now, you probably, good chance you recognize this one as well. This is water. But chemists could call this something else, but they don't. We just call it water. Everybody just calls this water. However, if you looked at the system of nomenclature just here, and these are both non-metals, we could name this. And in this case, this would be 2 hydrogens, so dihydrogen. And then 1 oxygen, and being that it's the second element, we got to include that mono. So this is monoxide. Dihydrogen monoxide is our technical name for water that almost nobody uses. And because almost nobody uses, you can get and have a lot of fun with this. So if you check out dhmo.org, you'll find out all sorts of lovely information out about water that you didn't know, how it causes cancer. So that people who drink this, they all get cancer. Things of this sort. It's kind of a parody of a site. But check it out. It's a little humorous, and you'll find out that some intelligent people have been fooled into thinking that we need to ban DMHO and stuff like this. It's pretty amusing. So we actually pulled this off and convinced some teaching assistants one year to sign a petition to ban DHMO from the university. We told them that we used it in the labs, even though it causes cancer. That 100% of people who've ever drunk this get cancer. So, and things of this, or I should say it backwards. Everybody who's ever had cancer has drunk this. And we just use it at the university in our chemistry labs because it's cheap. Things of this sort. So hardly ever used, but definitely worth taking a look there. This is molecular nomenclature. It is a beautiful thing. I love this. This is superior. It's much easier to go from formula to name as well as name back to formula. Here's the problem, though. As students, we've now taught you 2 sets of rules for 2 different types of compounds. Students want to mix up the rules. So if you recall, a little bit ago, we named an ionic compound here MgCl2. And it was a metal with a nonmetal. If you named this as a molecular compound by accident, you might call it magnesium dichloride. Nope, that wouldn't work. This is just plain old magnesium chloride. We don't use those number prefixes on ionic compounds. So I just wanted to return to ionic nomenclature for just a brief second to show you the most common mistakes students make in naming. So again, don't apply the molecular rules to ionic compounds and don't apply the ionic rules to molecular compounds. Okay, so now we got to name 2 different types of acids, and the first is called binary acids, and binary acids generally just are composed of 2 elements, hydrogen and one other. And it doesn't mean there's just one hydrogen atom in the formula. There could be more than one, but there are just 2 elements in your typical binary acid. And so I want to start with the most famous acid of all time and the most famous binary acid, one you might already know the name of. And again, if we start with one you know the name of, it makes it easier to kind of learn the method here, the system of nomenclature. So in this case, HCl is hydrochloric acid. And so it turns out on any binary acid, you're always going to put the prefix hydro on it. Ic, acid is what you'll end it with. And what goes in the middle just depends on what that other element is. For chlorine, you put chlor right there. So this is hydrochloric acid. So in this case, this is your lovely acid that's in your stomach. It's the stuff you pour in your swimming pools. Now the stuff in your swimming pools, usually you're pouring that in. It's way more concentrated. So don't think like, I'm just going to help digest my food by drinking a little of this stuff. Doesn't work that way. Way more concentrated and definitely going to cause you some serious problems, possibly death. So don't drink pool acid. Main story here. But super common acid here. One of the most common ones we'll use in titrations in a chemistry class and stuff like that as well. Now, if we take a look at what we've set up here for these other 2, we know that we just need to put hydro, save some room, ic, acid for both of these. Hydro, save some room, ic, acid. And just what's the something that goes in there? And so for sulfur, it turns out we just put sulfur in there. And so this is hydrosulfuric acid. So not to be confused with plain old sulfuric acid, which we'll find out is actually a different acid. This is hydrosulfuric acid. And then Se here, you might not know the name. So, and it's not even one of the ones I told you probably should memorize, but that's selenium. And so this is hydroselenic. So, and there we've got hydroselenic acid. Cool. These are binary acids, and as long as you've got the pattern down, and again, good chance you know the pattern from hydrochloric acid, you should be good to go. The confusion comes when we mix in the rules for oxyacids in a second. Sometimes they're also called oxoacids. So, and we just don't want to confuse the two different systems between the two different types of acids. So now we've got to name our oxoacids here. And again, an oxoacid starts with hydrogen, just like the binary acids do, but instead of having one other element, it has one of those polyatomic ions off that list you're supposed to memorize. And so in this case, this is the binary acid associated with the nitrite ion. So, and very important if you memorize this, that you know it ends with an ITE for ite. So, and this is the binary acid of the nitrate ion. So, and again, very important that you know this ended with an ATE. So also notice the charge. Because these are -1, it turns out that hydrogen essentially is +1 in these formulas. So, and it turns out it's not really ionic, but it kind of has the equivalent of having a +1 charge. So, but these are all non-metals, so we really couldn't call this ionic, but hydrogen's kind of the equivalent of +1, and that's why there's just one of them here. If nitrate is -1, hydrogen's +1, that's just one of each. Cool, you'll see that other binary acids might have more than one hydrogen to balance out that charge. All right, so it turns out when you're going to name an oxoacid, if you already know your polyatomic ions names, you memorize those, it'll make your life a little easier here. So, because you're just going to turn ate into ick, like you ate something disgusting and said ick. So, and in this case, these don't start with hydro like the binary acids either, no hydro. So we're just going to, instead of saying nitrate, we're going to say nitric and then add the word acid to the end. And that's the one here. So this is nitric acid. And once again, ate turned into ick. So the suffix ate on the polyatomic ion turns into ick. So, and then this guy right here, the ite is going to turn into an OUS, an us. And so this is nitrous acid. The ite becomes an OUS when you name it as an oxoacid. So I like to say that you ate something disgusting and said ick, and then you got appendicitis. I don't know. So best I could do. But end of the day, you do got to memorize your polyatomic ions, and you do have to be able to then properly name these oxoacids. Cool, let's do a couple of more here. So it turns out for most of the oxoacids, you'll find out there's usually two versions. So, and the one with more oxygens will end up with the ick, the one with fewer oxygens will end up with the us, and life is good. But you'll find out that for chlorine, bromine, and iodine, these guys right here, they don't have just two oxoanions, the two of these polyatomic ions with oxygen, they've got four. And as a result, they don't just have two oxoacids, they also have four. And so they had to get a little bit more creative with the names. So let's take a look at that. So here we see for chlorine, we've got 4 oxoacids and 4 corresponding oxoanions. Now, full disclosure here, I want to make you realize that for ClO, oftentimes you'll see this written as HOCl-, and it turns out they do that because the hydrogen actually here is bonded to the oxygen. And they sometimes do the same thing here. Instead of writing this as ClO-, sometimes they write this as OCl-. Just want to make sure if you saw it that way, you weren't confused that it was something else. Same thing, same thing. Now, in this case, it turns out they took the middle two and did the same thing we looked at for, most of the other oxoanions where there was only two, like nitrate and nitrite. And the one with more oxygens was the 8, and so they made this chlorate. That is the chlorate ion. So, and then this guy is the chlorite ion. And so then they had to come up with names for the extremes here. So how do I tell students, or how do I tell people in general, that this guy has more oxygens than chlorate? So, well, it turns out they're going to use hyper as kind of a base. Like hyper means above or beyond, like when you're hyperactive. So you got too much energy and stuff like that. So, and how do I tell people that I've got fewer oxygens than chlorite? Well, that's when they're going to use the prefix hypo. Like when you're hypoglycemic, that means you have low blood sugar. Hypo means low or below. And so how do I say that I've got lower number of oxygens than chlorite? I say hypochlorite. Let's get those on the board here. So fewer oxygens than chlorite, hypochlorite. And again, more oxygens than chlorate, we should say hyperchlorate. And herein we have our first dilemma here. So it turns out the lords of chemistry, back when they were doing nomenclature, they looked at this and they're like, this is just too easy. You know what? It'd be fun if students got stuff wrong more often. So you know what? Let's just take the H and the Y off that guy right there. And let's just call it perchlorate ion, not hyperchlorate ion. And that's what they did. So, and the truth is, I don't actually know the where that actually came from and where the HY went, or if there ever was an HY, or if per means the same thing as hyper, or what that is. I'm making this up. So, but that is the perchlorate ion, not the hyperchlorate ion, FYI. Cool. Now, if we go back from these and go to the oxoacids, again, 8 is still going to turn into ic, and ite is still going to turn into us. And so in this case, HC, well, let's just start with the middle two again. Chlorate is chloric acid. So, and chlorite becomes chlorous acid. Oh, let's make sure we get that word acid on there. So, and then HClO or HOCl, and I shouldn't put a minus there, but HOCl, instead of being hypochlorite, this becomes hypochlorous acid. And then perchlorate is going to become perchloric acid. If I can spell correctly, that would be awesome. Cool. And that is how we name oxyacids. Cool. And if you look, I see I actually put a couple extra on your handout there, your study guide. So let's get those on the board here. So we got H2SO3, H2SO4, and you might know that SO3 2- is sulfite, and SO4 2- is sulfate. And so the ite becomes an us, and it turns out when they go to the acid, they also add the UR in there. This is not just sulfus acid. They call it sulfurous acid. And this is not just sulfic acid, it's sulfuric acid. And if they really want to trick you on a multiple choice question, notice they might have you doing either H2SO4 or back to one of our binaries, H2S. If you recall, H2S was hydrosulfuric acid, whereas H2SO4 is sulfuric acid, and that can be pretty darn confusing. Cool, but this kind of closes out our lesson on nomenclature. And again, we got 4 systems here. So ionic compounds, molecular compounds, binary acids, oxyacids, and that's where the confusion lies. Having 4 different ways of naming things, you got to know which of the 4 types of compounds you have, and then which of the 4 systems of nomenclature to use. Cool, if you found this lesson helpful, please consider giving me a like and a share. And if you're looking for tons of practice problems and the study guides that go with this, check out my premium course on chadsprep.com.